Assalamu alaikum. I welcome you all to another lecture on linear circuit analysis. In this lecture, we will discuss how to calculate the initial conditions of the circuits containing the energy storage elements, which are the inductor and the capacitor. So let us start with this lecture. We need initial conditions containing inductances and the capacitors. So we'll replace all the capacitors with an open circuit. We'll redraw the circuit and replace all the capacitors with an open circuit, and we will replace all the inductors with the short circuit. Once you have redrawn the circuit, then you can apply basic circuit analysis to find out the voltage across the capacitors and the current flowing through the inductor. And these values will be the initial conditions of those elements. Remember that the initial conditions are important to understand the behavior of the circuit in a transient state, as well as they are important to create the particular solution out of a general solution of a first order differential equations. So let us start with some examples, and then we will summarize the concepts covered in this lecture. We have a circuit here. So let us say for this given circuit, we need to find out Vc0 plus and IL0 plus. This is IL and this is Vc. So to find out the Vc0 plus or IL0 plus, we require to find out what is Vc0 negative and what is IL0 negative, because the current through an inductor cannot change abruptly, and so for the capacitor the voltage cannot change abruptly, and therefore finding out the initial conditions will solve for these two unknowns required in this given numerical. So we will redraw the circuit. Step 1, we will redraw the circuit at t equal to t less than 0. Remember that this will open at time t equal to 0. So for t less than equal to 0, this circuit shall be of the shape. So we have this is 10, this is 2. We will replace this with an open circuit. So this will constitute Vc0 negative. Here we have this 3 ohm resistance, and this inductor is replaced by a short circuit here, and this is IL0 negative here. So now it is a very simple linear circuit analysis problem. This IL0 negative equals to V divided by the total resistance in this path, and that is this 2 ohm plus this 3 ohm. So that constitutes the value equals to 10 divided by 2 plus 3, and that is equal to 2 ampere. So now that we have calculated the value of IL0 negative, so this IL0 plus equals to IL0 negative, and that is equal to 2 ampere. As far as the voltage across the capacitor is concerned, we do notice that this capacitor has this node A and this node B common with the 3 ohm resistance, and therefore the voltage across the 3 ohm resistance is the voltage across the capacitor, and therefore I can say that Vc0 negative equals to the voltage across this 3 ohm resistance, and that is equal to 3 into uh, 3 into IL0 negative, and that is equal to 3 into 2, and that is equal to 6 volt, and that is the voltage at Vc, that is the voltage at Vc0 plus here. So you can see that it is very easy. Once you redraw the circuit, you replace the capacitor with an open circuit and you replace the inductor with a short circuit. Thereafter it's just the application of the basic circuit analysis methods to find out the voltage across the capacitor and the current through the inductor. Next, we will solve another numerical here, and we will see what else we can find out once we calculate the value of the initial conditions. So let me draw a circuit here. However, because it's a current source, so we cannot connect a single pole, single throw switch with this current source. Rather, a single pole double throw switch will be used. So once we have this switch will move from this position to this position, and that will create a shorted path across the 2 ampere source after time t equal to 0. And that is perfectly okay, because for the current source we cannot afford to have an abrupt disconnection. Therefore, if we want to disconnect this current source from the circuit, we need to provide some alternate path for the current source to keep flowing the current according to its own ratings. So first of all, let us find out what is IL 0 plus and what is VC 0 plus for this given circuit. So for this, we have to do we have to redraw at t less than 0. So at t less than 0, if I redraw the circuit, I am left with an open circuit here. This will constitute VC0 negative. This 1 ohm resistance, this inductor is a short circuit. This is IL 0 negative, and here we have this is 2 ampere source, and this is the circuit here. So as you can see that this current, this path, this is an open circuit here. This is an open circuit. So therefore, this IL 0 negative is equal to 0 ampere, and that is also the IL 0 positive, or the instantaneous or the current right after you close the switch. For this VC0 negative, because this 2 ampere current source is only flowing in this direction, so we have a plus, we have a minus, we have a 2 volt across this 1 ohm resistance, and therefore we can apply a KVL here to find out what is VC0 negative. So VC0 negative in this polarity is minus VC0 negative minus 2 volt equal to 0. So VC0 negative, that is equal to VC0 positive, is equal to minus 2 volt here. So this is the initial condition we have calculated through this given circuit. However, we can find out something else from this given circuit, and that is, if we want to know what is the rate of change at which the capacitor voltage will change or the inductor current will change right after time t equal to 0, we can calculate it using this information. So let us find out. Let's calculate dVC 0 plus over dt and DIL 0 plus over dt. So one thing is the rate of change of the capacitor voltage, the other one is the rate of change of the inductor current. So we have to redraw the circuit at time t greater than 0. So redraw the circuit at t greater than 0. So this is the circuit here. So we have this source 10 volt, it will connect it with this through this 2 ohm, it will be connected with this capacitor here. This capacitor has a connection with the inductor through this resistance. This is 1 Henry, this is 3 ohm, and here we have a voltage equals to minus 2 volt before the switch was moved or switch was operated. So right now we do know that in order to find out dVC over dVC 0 plus over dt, we do know that IC equals to C dV by dt, and therefore dV 0 plus over dt equals to IC 0 plus over C here. So the value of C is known, that is equal to it is half farad. So the only thing we need to calculate is IC 0 plus here. Now IC 0 plus, how can we find out the IC 0 plus? So IC 0 plus equals to this voltage minus this voltage divided by this resistance R. We don't have any current flowing here. This I 0 plus is equal to 0 because there is an inductor in this path, and inductor opposes sudden change in current. IL 0 negative is equal to 0 ampere, and therefore IL 0 plus is also equal to 0 ampere. So the current will only flow through the capacitor at time t equal to 0 plus. So IL 0 plus equals to 10 minus 2 divided by 2, and that is equal to 6 ampere. So if I plug this value in here, therefore that will become dV C 0 plus over dt, that is equal to 6 divided by 1 by 2 farad, and that is equal to 12 volt per second, and that is the rate of change of the capacitor voltage after we operated the switch at time t equal to 0. So the capacitor will have to traverse to its final value at initially at this rate, which is equal to 12 volt per second. Now we can also find out what is the rate of change of the inductor current DIL 0 plus over dt, and that we can calculate by using the expression for the voltage across the inductor. So therefore we do know that VL is equal to L DIL 0 plus over dt. This implies that DIL 0 plus over dt is equal to VL over L, and that is, we need to find out the voltage right after the switch, voltage across the inductor right after the switch is operated. So what is VL 0 plus? If we apply, if we see on look onto this circuit, this is the voltage VL 0 plus here. So if I apply the KVL here, this KVL, we can safely say that this is equal to minus into minus 2 plus 3 into IL 0 plus VL 0 plus, that is equal to 0. So we have VL 0 plus equals to 2 volt here. So with this thing in mind, if now if I substitute this value in here, so then this will become equal to DIL 0 plus over dt equals to VL 0 plus divided by the inductance. Inductance is equal to 1 Henry. It is equal to 1 Henry, and this thing we have calculated to be equal to 2 volts. So that is equal to 2 divided by 1. So that is equal to 2 ampere per second is the rate at which the inductor current will change at time t equal to 0 plus here. So only by calculating the initial conditions, a lot of other factors can be calculated. So before we conclude, we can summarize this in terms of the circuit elements, and that will be very easy and helpful to remember and understand the behavior of the energy storage elements. So if we have an inductor at time t equal to 0 plus, if this inductor has no charge, it will act as an open circuit, and at time t equal to infinity, the inductor will be replaced by a short circuit here. If an inductor has a current flowing through it, for example, we have some initial current flowing here, then that will be replaced by a current source of the value equals to I naught, and at time t equal to infinity, this will be replaced by a current source as well as a short circuit here, like this. The capacitor on the other side, if it is an uncharged capacitor, meaning that we don't have any voltage across the capacitor, at time t equal to 0 plus, it behaves like a short circuit. However, at t equal to infinity, capacitor becomes equal to an open circuit here. This is equal to open circuit. However, if the capacitor has some voltage across itself plus V naught here, then we have a voltage source equation equated at time t equal to 0 plus, and this thing can be combined with this open circuit here, and that is the V naught, and this represents the behavior of a capacitor at time t equal to infinity. So at time t equal to infinity, the capacitor is an open circuit, but it still have the voltage across itself. At time t equal to infinity, the inductor is there, it will act as a short circuit, but if there is a current flowing here, that current will be represented by this current source I naught here. So I hope this lecture will clear the doubts about the calculating the initial conditions. Remember that the initial conditions are very important to analyze a circuit for its dynamic performance, whether it is a first order circuit or a second order circuit. So I hope the lecture is clear. Thank you very much. Allah Hafiz.